Hello, this video is on acyl chlorides, sometimes called acid chlorides. And you see on the right hand side a monomer of the molecule, and we've got a carbonyl group as usual here. This is a chlorine atom connected to the carbonyl chloride, and we've got in this case a CH3, a methyl group attached to the carbonyl carbon. So you can see it's like a carboxylic acid, which would have an OH group instead of the chloride. That's why it's called acid chloride sometimes, but strictly it's called acyl chlorides. So what we're going to do when we study acyl chlorides is we're going to just look at how to name them. We've sort of done what are acyl chlorides already just now. Then we're going to have a look at some reactions. We're going to look at reacting acyl chlorides with water, alcohols, ammonia, and primary amines. And then we're also going to have a look at the reaction mechanism for those reactions, which is nucleophilic addition elimination. So first of all, what are acyl chlorides? Well, we've had a quick look at them, and we've seen that they are alkyl group with the functional group, which is COCl. That's how we write the acyl chloride. And let's have a look now at, actually just before we do, let's give ourselves the general formula. The general formula of an acyl chloride is CnH2n take 1, and then we get the OCl part of the functional group as well. That's the general formula. Now let's have a look at naming a acyl chloride. Start off from the displayed formula, and naming them is rather like naming carboxylic acids. The first thing we're going to do is number our carbons, and we're going to carbon number 1 is the carbonyl carbon, and so then we're going to take the longest chain and number along it. So we get our numbers like so. But we notice that we've got a methyl group here of carbon 2 and another methyl group here of carbon 3, so we'll have to name those in the end. But let's start with a name. Acyl chlorides always have the part, they finish like OL chloride. They always finish like that. Alright, so we can write that down first if we like. OL chloride. And then the preceding part of that name depends on the length of the carbon chain. So we've got 5 carbons, that's pent. All right, so pentan-OL. Pentan-OL chloride. So it's something pentan-OL chloride. If it wasn't for those methyl groups, that's what it would be. And so we just have to precede that part of the name with the 2 methyl groups. So we've got 2,3-dimethyl. Pentanol chloride. So let's write that down. 2, 3 dimethyl pentanol chloride. That's how we would name that acyl chloride. So let's have a look at some of the chemical reactions of acyl chlorides, and we're going to start off with water. And what we're saying here is that they're going to react vigorously with cold water. In fact, it doesn't even have to be room temperature water. But even with cold water, they react vigorously, and they're going to make a carboxylic acid. And so let's have a look at an actual reaction. So let's do ethanol chloride. So like we named it in the previous slide, we'll be able to work out what the displayed structure is from this name. So we're going to have the functional group, of course. We can draw the functional group like that, and so then the next part of the clue comes from ethan, and so that's going to mean that we're going to have 2 carbons, one of which we've already got, so we just add the second one, saturated with hydrogens, and we have our ethanol chloride. So if we've got our ethanol chloride there, and we're going to react it with water, like this, what we're going to get is a carboxylic acid, and we're going to get ethanoic acid in this case, because the two carbons don't go anywhere. So let's quickly draw out our ethanoic acid, like so. And you'll notice that we've lost a chloride and we've added a OH group, but we've still got a hydrogen from the water to account for, and that appears with the chloride, like so. And this is ethanoic acid. And we've got hydrogen chloride there as well. And a couple of things about this reaction. Let's just paint over that chloride there, and that's where the chloride goes. If we were to draw out our water molecule, like so, we would see that one of the hydrogens of the water molecule goes off with the hydrogen chloride, and the hydroxide group in purple becomes this hydroxide group here on the ethanoic acid. So that's tracking a few of the bits of the molecules and where they go. The other thing to say is that hydrogen chloride, as it comes off in this reaction, is a gas, and you're going to see those gases as white fumes. Here's a picture of it here, like this. So you've just added the ethanol chloride in the dropper here, in this dropper, to some cold water, and you can see what looks like steam in this photograph, but that's actually hydrogen chloride gas coming off. So this will be done in a fume cupboard. The glass rod is just for stirring purposes, and there you have it. That's its reaction with water. Let's now look at our reaction of acyl chlorides with alcohols, and they react vigorously as well. At this case, the vigorous reaction takes place at room temperature, and when we add ethanol chloride, so let's draw out ethanol chloride again, like so, and we're going to react it with methanol this time. So let's draw out methanol, and we say we're going to produce an ester this time. So the ester we're going to produce is methyl from the alcohol, ethanoate from the acyl chloride, and we're going to draw it like this. Our ester link and the rest of our methanol molecule, just completing the hydrogens to make it look a little bit neater. Let's do the rest of them as well, and then what we can do is just track a few of the bits of the molecules. Of course, we've got to account for the chloride and one of the hydrogen, and just as before, we get hydrogen chloride coming off as well. And so what we can do is we can say that during this reaction, this bond breaks here, and the H+ ion comes off because the oxygen keeps that both of those bonding electrons, and this bond breaks off here, and the chloride takes both of those bonding electrons, and they make the hydrogen chloride here, and the methanoate ion that is left, that is this ion here. Methanoate ion is what adds on to the remaining bit of the alkyl chloride to make the ester. And so let's name everything as while we're at it. So we're going to name the ester as methyl ethanoate. Methyl ethanoate. This is the methyl bit, and this is the ethanoate bit. And of course, we started with ethanol chloride and methanol, which we don't need to name, I don't think. Okay, so that's what you need to know about the reaction. We'll do the mechanism later on in this video, but let's move on to reaction with ammonia. So when acyl chlorides react with ammonia, the reaction is also vigorous, but just like with alcohols, it's at room temperature. So at room temperature it's vigorous. And when the reaction takes place, we produce an amide, which is a carbonyl group with an NH2 on it instead of the chloride. So let's have a look at the actual reaction. Save a little bit of time, I've drawn out our ethanol chloride, and to our ethanol chloride we're going to react ammonia. Let's draw a displayed structure of ammonia. We can draw it like this if we like. And what we're going to get is an amide called ethanamide. So the amide you might know is like this, where our NH2 instead of our chloride, and we've still got our methyl group on the other side of our carbonyl group, like so. Now let's see what we've got. We've also got HCl again, as with the previous two reactions. Let's track our molecules. So the chloride that was on the ethanol chloride has found its way to being on the hydrogen chloride molecule. One of the hydrogens that was in the ammonia has joined it in the hydrogen chloride molecule, and the rest of the ammonia molecule has replaced the chloride part of the ethanol chloride here in the ethanamide. So let's name that. That's ethan, because we've got two carbons and it's got an NH2 group. The NH2 group here, I've just underlined again, is on the carbonyl carbon, and that makes it an amide, so it's ethanamide. You'll be learning about amides separately, so we'll dwell on the naming of amides more in that video. But for now, that's what you need to know about acyl chlorides reacting with ammonia. Our last reaction that we want to study is that of acyl chlorides reacting with primary amines. Now, primary amines, and in case you haven't done primary amines yet, so an amine is going to be like ammonia. Ammonia is like the first amine, but with one of the hydrogens substituted with a alkyl group. In fact, it could be more than one of the hydrogens. So a primary amine would have an R group, one R group, and two hydrogens. Whereas you'll recognise that with ammonia, the R is just a hydrogen. So this is a primary amine, and when you do amines, you'll see that a secondary amine would be two R groups on the nitrogen, and a tertiary amine would be all three hydrogens being replaced with various alkyl groups. So that's a primary amine, and what we want is we want a reaction with our acyl chloride, ethanol chloride again, and this time we're producing an N-substituted amide. Right, so remember that the amide has this functional group. That's what makes it an amide. And N-substituted just means that one of these hydrogens is going to be replaced by an R group, like that. So that's an N-substituted amide, but again, you'll do more of that in more detail when you cover amines and amides. But for now, we're going to just draw out the reaction. So let's start off with our ethanol chloride again, and we're going to react it with methylamine, right, which is a primary amine. So let's name it methylamine. All right. So I've told you that an amine has an NH2 group. So let's draw an NH2 group like that, and instead of one of the hydrogens, it's got an alkyl group. In this case, our alkyl group is a methyl group, so we can draw our methyl group like so, and that's our methylamine. And so when they react together, you're going to get N-methyl ethanamide. So let's I'll name it down here because I don't want to overwrite the other bit. So it's N for an N-substituted amide, and it's still methyl, N-methyl ethanamide. Like that. So let's draw out our product. So again, like in the other reactions, we're going to lose one of our hydrogens. Let's say we're going to lose this one, and to draw the molecule we just need to flip the amine over to draw the right hand side of the molecule. So it's going to be like so. So our nitrogen hydrogen is like that. We're going to draw our methyl group off to the right, so you can see we just flipped it over 180 degrees. And instead of that nitrogen being bonded to its other hydrogen, it's now connected to the ethanol chloride, or the rest of the ethanol chloride without the chloride. So it would be connected to the carbonyl carbon, like so, and the rest of the molecule is just a methyl group like this. Okay, and so that's our product, and we get the HCl again. And as we've done before, let's track our Cl. That was our Cl there in our ethanol chloride, and that's appeared in our hydrogen chloride molecule. And the hydrogen that I circled previously is that hydrogen that joins it in the hydrogen chloride molecule, and the two remaining bits of the molecules join together around the carbonyl carbon and make our N-methyl ethanamide. And just explaining where that name comes from, this is our N-methyl part of the molecule, so N-methyl here, which is what comes first. That's what we've added on to our starting molecule, and this is the ethan bit because we've got two carbons, so it's ethan amide. It's an amide because we've got that amide group hanging off it, and the type of amide we've got is an N-methyl ethan amide. Okay, and let's finish up with the actual reaction mechanism, and in fact this is the most important part of the lesson. We're going to use an example, a real example, so we can use ethanol chloride again. And we're going to need a nucleophile, and we're going to use methanol as a nucleophile. So that's going to be our nucleophile. And if you remember, a nucleophile is a molecule with a lone pair to donate. It's usually electron. It's got an excess of electrons, and it's looking to share its electrons in the form of a lone pair. So that's the nucleophile, and it's going to attack our ethanol chloride. So here's our ethanol chloride molecule, and always first we need to put the partial charges here on our carbonyl group, and then we're going to have a methanol molecule that's going to attack that delta positive. So let's draw out our methanol molecule in such a way as to show its lone pair, because we need the curly arrow coming off the lone pair. So we can draw methanol like this, and oxygen has got two lone pairs, one of which is going to attack this partial positive carbon atom. So that's good, that's the first thing, and as that happens, then the carbonyl carbon decides it's got too many electrons around it, and the oxygen says, well, I quite fancy electrons, and so the electrons in one of these bonds make their way over to the oxygen, like so. And then we just draw out what we've got. So we've still got the original methyl group, but now the carbonyl carbon just has a single bond to the oxygen. That oxygen had 2 lone pairs, as it always does. It's got 3 lone pairs because those last 2 electrons I just drew were the ones that were in the double bond. So now it has both of those electrons instead of just one, and that gives it a -1 formal charge. The chlorine is still on at this stage, but now the methanol molecule has attached itself to the carbonyl carbon. Now that oxygen atom from the methanol, it has donated, let's say, one of its electrons in the lone pair to that carbon now, and so we can give it a plus formal charge. It's a 1+ formal charge now, and we'll track the electrons. Why don't we track the electrons in red? So starting on the left, let's take this lone pair that I've written in red. They become this bond. So oxygen used to have both of those electrons when they were in its lone pair, and now it's sharing one of them with carbon, and so that's where the +1 formal charge comes from. Let's change colour. Let's do this one in green. So these 2 electrons that made up this pi bond have made their way onto the oxygen, and so I think I said when I was talking that it was this lone pair here. It could be any of the 3 lone pairs, so whereas before one of those electrons was really carbon's electron, now it's oxygen's electron, and that gives the oxygen that that -1 formal charge. Okay, so what happens next is that chlorine fancies a bit of all this electron business, and so chlorine is going to take the 2 electrons in this bond for itself. And as that happens, the carbon says, well, hang on a minute, I'm a bit short of electrons now, and so one of these lone pairs reforms the double bond. So let's say it's this lone pair, and they come back and make that double bond. And so then we're going to draw out what molecule we get there. So let's methyl group unaffected. So we've still got our methyl group to the left of our molecule. Now our carbonyl carbon is got its double bond to oxygen back, and oxygen that was in our methanol molecule we draw like so. We haven't dealt with this formal charge yet. All we've done is got rid of the chloride rather. So as we did before, let's just take time and track some electrons. Let's track these 2 electrons first, shall we? This double bond here, this pair of electrons in that single bond there have made their way onto the chloride ion as it is now, because it's got an extra electron, and that gives it a -1 formal charge, because it was sharing essentially one of those electrons used to be with the carbon atom, and now it's with the chloride ion, so that gives it a -1 formal charge. And let's choose a different color. We're going to go to browny color now. Let's track this lone pair here has made this double bond here. So we've tracked those 2 little changes there and drawn out our molecule. When you're answering an exam question, you don't have to do this last bit of tracking of electrons. That's just to help us cement the reaction mechanism there. So now let's deal with the oxygen that has the +1 formal charge. And as you know, oxygen is electronegative in the first place, but in the absence of electron, it's even more hungry for electrons. And so where's it going to get it from? The methyl group or the hydrogen? Well, it's going to attack the hydrogen. And what happens is the electrons that are in this bond, right, are grabbed by the oxygen. And so let's draw that down here. So we've still got our straightforward methyl group, and we've still got our carbonyl group, but now we have an ester, because that oxygen retains the CH3 group but has lost that hydrogen. So that hydrogen goes off like so. So as we've done before, let's track some electrons. Go to light blue. Now these electrons that were in this oxygen-hydrogen bond have now replaced oxygen's lone pair, like so. And that's the only change. That's the only change for that little step there. And that because oxygen has taken both of those electrons that were in that covalent bond, the +1 formal charge disappears. Disappears from the oxygen, that is, and hydrogen leaves without an electron, which is a hydrogen ion or a proton, like so. And what we have is, like we said, we have an ester, and this is methyl ethanoate, this being the methyl bit, this being the ethanoate bit. So we can write that out. Methyl ethanoate. And of course the hydrogen ion is also left there. So that's the reaction mechanism, and you count, I think, 5 curly arrows. And with nucleophilic addition elimination, that's always the same, 5 curly arrows. And if you want a little memory aid, there's sort of 3 words that you can remember, if you like. The first one is addition. All right, so we've added our nucleophile, in this case methanol, to our acyl chloride. That's the first step. Then we eliminate, and we eliminate the chloride. It might be a chloride, it could be another halide, because you know, you could get any sort of acyl chloride to start with, or acyl halide. So that's the second word to remember, and then you deprotonate. Then you deprotonate, and there's sort of like the 3 steps, if you like, that account for the 5 curly arrows. And if that helps you to remember the mechanism, I hope it does anyway. But that's it. That's all you have to do. We'll get plenty of practice on that, and it'll become second nature to you. So that's finished the lesson on acyl chlorides. We've worked out what they are, and we've looked at their reactions, and we've looked at the mechanism as well. So hopefully that's all been clear. We'll get some practice on other examples of the same mechanism.